Very good afternoon to all the attendees, and welcome to Professor Patrick Das Gupta, who is the speaker for today for this special public webinar, which is being organized as part of the School Outreach Program, jointly organized by the National Academy of Sciences India Delhi chapter and the India Qualified College under the aegis of DBT Staff College Program. He'll be talking to us today about mysteries, clues, surprises, and creativity in physical sciences. And Professor Patrick Das Gupta is from Department of Physics and Astrophysics, University of Delhi. And before inviting him to share his screen, I also would like to thank Professor Anurag Sharma and Professor Ajoy Khattar for giving us this opportunity to host the school outreach program for more than 80 schools from all over India who are participating in this particular an year-long activity. And I also would like to thank all the teachers from these participating schools for motivating the students from class 9th to class 12th to participate in this program. Professor Das Gupta, I'll stop sharing now.
All right. So what I will do is,
sure.
I will start sharing my screen. Is that all right?
Yes, absolutely, sir. Yeah. Absolutely.
Yeah.
And I request all the attendees to kindly type out the questions in the chat section.
Are my slides visible?
Yes, sir. You can put them up in the slideshow.
Yeah, I will now go into the presentation mode.
Sure.
So the full screen mode is visible to everyone?
Absolutely, sir. But I think we couldn't read the last line. Maybe the font size is...
I see. The last line, of course, is...
Yes.
Nasi,
did you see science promotion activities? We can hear.
Science promotion activities.
Yes.
The last line is August 2020.
Oh, that we are not able to
month
read.
And
yes.
year.
Yeah,
oh, I see. Probably what I will do is, one moment, I'll just try out something.
Yes, yes.
Now are you able to see?
Okay, sir. So the students, they are saying they are able to see. Maybe if you can click to the next slide, then we can see whether the slides
all
are
right.
moving.
All right.
Yeah, sure.
Is the last line visible on the understanding is the last?
Yes, yes, yes. Absolutely, sir.
Okay, great.
Please.
All right. So let me begin. So I'm very happy that Professor Manoj Saxena invited me to be part of this program, because it is very excitement about research areas to our young friends. Ultimately, our young friends are the future of this country. So I begin with the well-known question as to what is science. We all know that we human beings, we are endowed with more intelligence than other creatures on our planet. And because of our intelligence and memory, we start observing patterns and changes, cause and effect relations, whenever we look towards our natural phenomena. So for example, we know that early in the morning sun rises, then evening it sets, but then again next day early in the morning sun rises, it sets in the evening. So there is a particular pattern that gives us a sense of progress of time. Similarly, cause and effect relations which are very, very universal. And that is, you are able to listen to me because I am speaking. So my speaking is the cause, and you're able to listen to me is the effect. And cause and effect relations are universal in every aspect of natural phenomena. The subject of science is to study the natural phenomena in a very, very systematic manner, in particular, in a very quantitative manner, after making controlled observations, making quantitative models to understand the patterns, and then, of course, make new predictions based on the model to check whether the model is good or one should modify the model. So, for example, our ancestors, they had already figured out that when we observe day after day the position of stars, then in a given day, when we look at the position of a star, then the star appears to go around a fixed star. Today, a star is the so-called pole star or Dhruvatara. And if one continuously monitors the position of the stars throughout the night, one will see that the stars tend to move around the pole star in a circular manner. We know, of course, today what the reason is. The reason is that Earth rotates, and it so happens today the axis is Dhruvatara, and that is the reason why stars, they apparently move around the Dhruvatara, but in reality, it is not the stars which are going around the Dhruvatara, but it is the Earth which is spinning about its axis. Similarly, other pattern that we observe is that when our moon and sun are almost, then we see high tides in the ocean, while if they are orthogonal to each other, then there is a low tide. And similarly, in biological sciences, we know that our, one moment, the slide just got, we need to take apparently a non-living and region, moist soil from the sea. And after all, our ancestors had seen this pattern, and that is how agriculture developed and human civilization. The scientific method, scientific model begins with the observation of phenomena. The pattern is one makes a model or what is called a hypothesis. And how do we know that the model due to some reason, I had got muted at some point. Can one tell me where I had got muted? Hello, am I audible? Hello. Okay, very good. I'm audible. So I hope I explained the basis of scientific method or scientific model building, where you start with systematic observation or systematic experimentation of natural phenomena. Based on the observed pattern in a quantitative manner, one forms a hypothesis or a scientific model, and then to test whether the model is good, one makes a new prediction, and the prediction is tested experimentally. If the prediction is borne out by the new experimentation, then we know the model is good. Otherwise, the model has to be rejected and the model has to be again modified. So we go back based on the new experimental finding, which is our new observation. We modify our hypothesis, and then again, based on the modified hypothesis, we make a prediction and again test it. If the experimental test is borne out, the prediction is borne out by the test, then we retain the model. Otherwise, again, we include this new experimental data or observation and again modify our model. So this particular cycle is what is known as the, yes,
Professor Patrick. Some students, they are saying the screen is not visible.
That's very strange.
Yes, I am also not able to see your screen.
One moment.
Yeah, can you just share it again?
Yeah.
Yes.
Yeah, is the screen visible now?
Yes, sir. Now it's visible. If you can put it in the slideshow. Yeah.
Yeah. I'll just go into the full screen mode.
Yes, full screen.
One moment. Is the full screen
yes,
mode?
Absolutely clear, sir.
Yeah.
Please.
Yeah.
So maybe, sir, if you can go one slide in reverse, because I don't know, just 2-3 minutes.
Was this slide explained and was visible?
Students who are can just confirm whether this. Yes, sir. You can start from this slide, sir.
Yeah. So as I said, the patterns in the natural world, they motivate us to build scientific models, like going around apparent motion of stars around the pole star, that finally was explained by the rotation of Earth about its axis, or high tide, which comes about when sun and moon are aligned or oppositely aligned, while if the position of the sun and position of the moon are orthogonal to each other, then there is low tide. And similarly, when one plants an apparently inert seed into a fertile ground, it germinates into a fully active living plant that gave birth to the agriculture that essentially led to the civilization, human civilization. So all such patterns that are observed in nature, in a scientific study, one makes a systematic effort to observe and study the patterns in a quantitative manner. And based on systematic observations, quantitative patterns, one builds a scientific model. And from the scientific model, one makes a prediction. And if the prediction is borne out, then the model is correct. Otherwise, the experimental result is taken as a new observation and the hypothesis is modified. Again, a new prediction is made. And this cycle of scientific discovery goes on as a cycle. And that's the reason why science is never static. We always find newer and newer scientific theories, better and better scientific theories. What I will do is, I will give you an example to show how this method gave rise to several fundamental discoveries in physics. For example, we all know about gravity, and gravity was the first force that was understood in a quantitative manner. But it all began with the notion of our planetary system, sun, moon, and the planetary system. Since Earth goes around its own axis, all other objects, they have an apparent motion where they go around us. And naturally, our ancestors, seeing this pattern, thought that all objects in our cosmos, they go around our planet, that is Earth, and they developed this geocentric view that our planet is the most important object and everything must go around us. But then there were several surprises. If this model is correct, then everything, all planets must make regular movement around us. But it turned out two planets did not show this regularity. For example, Mars did not show this monotonic going around Earth. Sometimes there were retrograde motions of Mars, they were seen. So for example, the prediction of geocentric model was essentially violated by this retrograde motion of Mars. And therefore, a simpler theory of Copernicus was given, where Copernicus said that it is not the Earth around which planets go, rather it is the sun around which the planets go. But remember, Copernicus was giving a theory. But then you need observed data to support whether Copernicus is correct. And that is where Tycho Brahe and Kepler, they came in. Tycho Brahe had a fantastic, he was a Danish astronomer, and he had a fantastic observatory. So here is in this painting, Tycho Brahe has been portrayed sitting on this chair. He was an aristocrat, and he had his personal observatory, and he had recorded the positions of the planets in very accurate manner. He invited Kepler to study the pattern, the motions of the planets, and Kepler became an employee of Tycho Brahe in the observatory, and he made systematic study of the planetary motions. And the surprise was he came out with 3 laws. Today we call it the Kepler's laws of planetary motion. By studying the angular positions of the planets as a function of time, he built mathematical and geometrical model, and his first law said that all planets in our solar system, they move in elliptical orbits around the sun, where sun is lying on one of the foci of the ellipse. So Earth, for example, is going around in an elliptical orbit around sun, and sun is acting as the focus of this ellipse. The second law, which Kepler, from his painstaking study of motions of the planets, he realized by looking at the motion of the planets and looking at the time, he found out that if sun is at this point at the focus and the planet is moving about, when the planet is at the furthest distance, which is called the aphelion, the motion and the angular motion of the planet is very slow. While when the planet is very close to the sun, for example, the perihelion, which is the closest point, when the planet is near the perihelion, the planet moves faster. And in particular, what he figured out is that in equal intervals of time, if you look at the area swept about by the moving planet, as the planet is moving about the focus, in equal intervals of time, if you find out how much area this shaded bluish gray region is the area swept up when the planet moves from this point to this point, then this area is exactly equal to when the planet is at any other position in equal intervals of time. So when it is, for example, closer to the sun, in the same interval of time, it sweeps up an area, and this bluish gray shaded area is exactly equal to this bluish gray area. Although here the planet was moving at a slower orbital speed, while here the planet was moving at a higher orbital speed. So from the observations, he concluded these 2 points, that a planet of our solar system moves around the sun in an elliptical orbit with sun as the focus, while in equal intervals of time, the line joining the planet to the focus, this line sweeps up equal area in equal intervals of time. The final law, the Kepler's third law, was that because this is an ellipse has a major axis and the minor axis. For example, from the perihelion to the aphelion, this line is the major axis, and half of that is the semi-major axis. What Kepler found out is that the orbital period of a planet, that means the amount of time it takes to go from one point to back to the same point, that means the planet goes around full 360 degree, and the time required to go full 360 degree for a planet is called the orbital period of the planet. And what Kepler deduced by observing was that for any planet, the square of the orbital period is proportional to the cube of the semi-major axis. Here there is a printing error. It is not that square of the orbital period is equal to the cube of the semi-major axis, but it is proportional. So it's not equal to, but it's proportional. So Kepler's creativity, so remember, what are the things, the clues that Kepler obtained were from the observed data of Tycho Brahe, and the pattern he noticed were this geometrical pattern. So his creativity was to see this beautiful relations between period and the semi-major axis, the law that in equal intervals of time, the line joining the focus to the planet sweeps out equal area. This quantitative pattern that he saw, and his making them as laws in a quantitative manner, was his creativity. However, although Kepler's laws were for the first time someone was using geometry to explain a natural phenomena, that the first time geometrical quantities like ellipse, line, etc. were used to explain a cosmic phenomena like motions of planets around our sun. But someone might ask, why are these laws there to begin with? Is there a more fundamental law that can explain this creative ideas of Kepler? Today we know what the fundamental reason is. The fundamental reason is gravity. As you know, that gravity, that objects fall towards Earth, was always recorded. In fact, uh, one of the greatest Indian astronomers of all times, Aryabhatta, who gave his Aryabhatiya around 470 AD during the Gupta period, he was the first Indian to have realized that there is some force that keeps everything close to the surface of Earth. Similarly, before Aryabhatta, although it was not identified as a force, Aristotle was a teacher of Alexander, who invaded India and fought with Porus, who was one of the kings in the Peshawar region. This teacher of Alexander, namely Aristotle, he had given some laws, but his observations were not very accurate. For example, he had given the law that lighter objects fall towards the Earth at a slower rate than heavier objects. For example, he saw that feathers or leaves, when they fall towards the Earth, they fall at a slower rate, while a stone or a block of iron, when you drop them, they fall towards the Earth at a faster rate. And he gave this law that heavier objects fall towards the Earth faster. Although he did not identify as it due to gravity, but he had given this law. Galileo, who is considered to be the father of physics because he made very systematic observations, very accurate experimentations, and he got few of the laws of motion, which was polished later on by Newton in his 3 laws of motion. Galileo was the first to talk about acceleration, that velocities, when they change with time, there is something called acceleration. This was for the first time studied by Galileo. Galileo immediately had realized that Aristotle's law of falling bodies had a logical problem. What was that? So remember that how scientists, they show their creativity. When they observe something, they immediately realized that if you look at it from a new point of view, then it tells us something new. Either it can contradict the older law, or it can bring about a better insight into the laws. What Galileo, here is a cartoon of Galileo standing at the top of Leaning Tower of Pisa. What his logical argument was this: supposing you have a heavier body and you have a lighter body. Aristotle, of course, will say heavier body falls faster toward the earth, while lighter body falls at a slower rate. Galileo suggested what you do is you tie the heavier body to the lighter body by a wire, an inextensible wire. The combined mass now is bigger because heavier body plus lighter body weighs bigger than either of the two bodies. And therefore, if you drop the heavier body connected to the lighter body by this inextensible wire, then it must fall much faster than the first heavier body and the second lighter body. But this is contradictory because according to Aristotle's law, heavier body is falling faster than the lighter body, but the full object, according to Aristotle's law, must be falling much faster than the heavier body itself. And therefore, the combined system, which is heavier, which is falling much faster than the individual body, cannot be consistent with each other, because if the heavier body is falling at a lesser rate compared to the combined object, then it's a contradiction, because the combined object which contains the heavier body is falling at a faster rate. So this was a logical paradox which Galileo obtained, contradicting Aristotle's laws, and he immediately took upon himself to test it out by experiment. So he went to the top of the Leaning Tower of Pisa. He dropped two cannonballs, one, let's say, a cannonball weighing 5 kilograms and another cannonball weighing 20 kilograms, and he dropped them from the same height at the same time, and he showed to the people standing watching the entire experimentation that the two objects landed on the ground at the same time. Now comes, so Galileo showed that Aristotle's law of falling bodies is incorrect. Rather, from equal height, they land on the ground at the same time. Aristotle had made faulty observation. He had not realized that it is the air which makes the leaf or a feather fall at a slower pace, because the buoyancy or the air resistance which slows down. In vacuum, if you drop a feather and an object from equal height at the same time, they will reach the ground at the same time. Now comes Newton. Newton, he was an all-time genius, because not only he was a theoretical physicist, he gave theoretical laws, invented. He was a mathematician, he invented calculus and many other mathematical results. He was also a great experimental physicist. He was the first to show dispersion of light when you pass it through a dispersive medium like prism, and so on. It was Newton who actually understood the nature of gravity. And here, his creativity was to realize that when an apple loses its attachment from its tree, it falls to the ground. So an apple accelerates towards the ground. Newton realized that the moon going around the earth, after all, moon is going around the earth, and anything that goes around accelerates, because if an object is going around in circle, then we know there is a centripetal acceleration, v square by r. So moon going around earth indeed accelerates. He realized that the apple's acceleration when it is falling towards earth and moon going around earth is also an acceleration. Both the acceleration must be due to the common force, because Newton had already given his laws of motion where he had talked about force. What Newton realized was that fall of an apple, or for that matter, any object near the surface of the earth, and moon going around earth is also falling of moon due to earth. But he immediately realized that the acceleration of an object near the surface of the earth is much larger. If you measure it, it's about 9.8 meter per second square. While if you look at moon's angular speed, which is, as you know, the period of moon is roughly 28 days, and the distance of the moon is also known from the earth. So you can calculate the angular speed, and therefore you calculate the speed v. V square by r will give you the acceleration, and you can compute, and the acceleration is only 0.00272 meters per second square. So Newton immediately realized that moon is further away, and therefore its acceleration is small, while an object like an apple on the tree is at a distance much closer to the center of the earth. And from that, he deduced the inverse square law of gravity. All right. So the genius of Newton, his creativity was manifold. First of all, his creativity was to see that moon going around the earth is essentially moon falling towards the earth, just like any object that are dropped, they fall towards earth. And he made quantitative assessment of the acceleration, and he immediately realized the inverse square law of gravity, which said that if you take any two objects, and furthermore, Newton said that this gravity is not only existing due to earth, but gravity is universal. Anything that has mass causes gravity, and earth attracts, sun attracts. And in his Principia, he showed that Kepler's laws of planetary motion can be deduced by looking at the force that sun exerts on the planets, and he immediately deduced all the Kepler's laws of motion simply from the inverse square law of gravity that he proposed. Next level of understanding was due to Einstein. As you know, Einstein in 1905 had already given his special theory of relativity, where he completely overthrew the notion of space and time. And in particular, he showed that Newtonian laws of motion have to be modified. For example, velocities are not purely additive, but you have to include various other factors. Similarly, from one inertial frame, if you observe a meter stick which is moving with uniform speed, the meter stick will not appear having a length 1 meter, but it will be shorter, the so-called Lorentz contraction. Similarly, the clocks moving with respect to us in uniform speed will appear to run at a slower rate. So both time and space, they get modified when something moves with respect to us. And in particular, from his special theory of relativity, he showed that no physical object can move faster than the speed of light. But then immediately Einstein realized that Newtonian laws of gravity cannot be then correct. Why? Because Newton's gravity law says that the force between two masses, m1 and m2, when they are separated by a distance d, the magnitude of the force is g multiplied by m1 multiplied by m2 divided by d square. But supposing one object changes position now, that means d changes now, then according to Newton's law, the second object will immediately see a new force at the same instant, because the force is gm1 m2 by d square. If the d changes now, the force will also change now. But this cannot happen instantaneously, because the effect can propagate only at the best with speed of light. It cannot propagate with infinite speed. The change in the distance, this is the cause, and effect is change in the gravitational force. It can't be immediate, because nothing can move with infinite speed, or for that matter, nothing can move faster than the speed of light. So therefore, Newtonian gravitational laws are not consistent with special relativity. And it took Einstein 10 years to obtain a relativistic theory of gravitation, which is called general relativity. General relativity is nothing but a theory of gravitation that is consistent with special theory of relativity. But here, Einstein also, there was a base creativity. The creativity was this. As you know, Galileo's rule had already, Galileo's experimentation, etc., had already shown that the gravitational mass is same as inertial mass, because if you apply the Newtonian laws, which is mass into acceleration is equal to g into m1 m2 divided by d square, then the fact that Galileo says acceleration is independent of the inertial mass means that gravitational mass m1 must cancel with the inertial mass of the lighter object, and therefore inertial mass is same as gravitational mass. So Einstein, when he was trying to build a relativistic theory of gravitation, he was working very hard, but suddenly one day he realized one fascinating aspect. He was trying to find out, is there a frame of reference where no matter what the gravity is, you can simply make the gravity zero? Because remember, gravity is universal. Every object causes gravitational attraction. So Einstein was trying to see whether somehow you can screen gravitational force. And he was not able to do it, but then suddenly he realized that supposing I have a frame of reference, and if the frame of reference drops freely in this gravitational frame, then if I am in this freely falling frame of reference, I will not see the gravitational force. Why? Because inertial mass is equal to gravitational mass. In my frame, I am freely falling towards, let's say, Earth. In my frame, whatever object I have, they are all accelerating, having the same acceleration. So therefore, I will see that they are just floating about, or if they are having a in uniform motion, some motion with respect to me, they are moving uniformly as though there is no force. So this realization that gravitational force disappears in a freely falling frame of reference played a very important role in his mathematical formulation of general theory of relativity. In fact, Einstein later on said that the day he realized this, that was the happiest day of his life. Similarly, because of law of inertia, you can also generate mock gravity or pseudo gravity. So for example, I know that when I'm standing on Earth, the Earth with an acceleration 9.8 meter per second, second square. Okay. Am I audible?
Yes, absolutely, sir.
Yeah, because sometimes I get the message that the internet is unstable.
Yes, actually,
So
because
good
of
that
that,
internet is still
no,
there.
there is a certain lag between, maybe because of some poor internet connection. Yeah. But
Okay.
voice is breaking, but it is
But the
still,
slides are visible, right?
yes, 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 absolutely.
Yeah. Okay. Yeah. So now Einstein immediately realized that supposing I am in a rocket and the rocket is moving upwards with an acceleration 9.8 meter per second square, then if I am standing on the floor of the rocket, I will feel a gravitational like force pushing me down with the same acceleration 9.8 meter per second square. Okay, so if the rocket accelerates upwards with an acceleration 9.8 meter per second square, then I will feel exactly a gravitational like force pushing me down with a acceleration 9.8 meter per second square. In fact, if I'm holding a pendulum, the pendulum will also start oscillating. So these are the insight, these are the creativity which Einstein displayed, and using this creativity and is learning of a new mathematical tool which is called tensor analysis, he could create a relativistic theory of gravity, and that is how general theory of relativity was born. And some of the salient features of general relativity, I don't expect you to understand this, but this is just for the general knowledge. In Einstein's theory, gravity is not a force at all, but rather the so-called gravitational effects that we see are due to the fact that the space-time geometry is not Euclidean, but non-Euclidean. It is heavier objects like the Earth or the Sun, they cause warping of the space-time geometry, and this non-Euclidean space-time geometry is what appears as a gravitational force. So in other words, what Einstein showed in his theory is gravity is equivalent to the space-time geometry. So this is, of course, just to give analogy. One should not take them more seriously. Rather, supposing our space-time, instead of 3 plus 1 dimension, that is 3-dimensional space and 1 time, instead of 4-dimensional, supposing our space-time was 2-dimensional, then an heavier object would bend the 2-dimensional sheet, and more is the mass of the object, bigger is the deformation, bigger is the curvature, and so on. Similarly, on this 2-dimensional warp sheet due to a heavier object, if you take a test particle and throw it, it will not go in the Euclidean straight line, but it will go along a line that is not a Euclidean straight line, but nevertheless, it is the straightest possible line in this warped 2-dimensional geometry. So, as you very well guess, the new theory of gravity of Einstein, it predicts new things like bending of light, black holes, gravitational waves, and so on. So bending of light is simply this, because it's not the Euclidean straight line, but light will take the shortest path in this curved geometry, and therefore a light ray will get bent when it is moving close to a heavier object. And this prediction was the first to be tested around 1919 by a team of astronomers that was led by the astronomer Arthur Eddington, and it was shown that Einstein's prediction was correct. and Einstein immediately became a superhero. And because of bending of light, the gravitational geometry or space-time geometry can appear like a gravitational lens. Here is a cluster of galaxies, many galaxies bound together, and therefore it's a very heavy object, and therefore the space-time around it is bent. And further away, there is a source of light, and the light, when it is coming, it gets bent and it appears as a Einstein ring. As you can see, these are the arcs, which are the so-called Einstein ring. And the gravitational lensing has already been tested, that follows from Einstein general relativity. And recently, direct detection of the moving wave-like motion of the ripples of space-time geometry, the so-called gravitational waves, first time were directly detected in 2015 by the LIGO detectors, in which two black holes, when they are going around each other, because they send out this gravitational wave, they lose energy, they spiral towards each other and form a bigger black hole. And this was directly seen. And indeed, this was another confirmation of Einstein's prediction of gravitational wave. And today, we also have the foundation stone of a LIGO detector in India near Aurangabad, the so-called LIGO India project. After 2 or 3 years, will start becoming functional, and even in India, we will be directly detecting gravitational waves. The other effect here, because I've already spoken for a long time, it is more important that people ask me questions. So probably these are my last two slides. I will not talk anything more about quantum mechanics, but around 1904, developments around 1904 gave rise to a new field which completely upturned not only physics, but the world of philosophy, that is the so-called quantum theory, according to which particles going through two slits can show interference pattern as though they are waves. And quantum mechanics showed that without quantum mechanics, atoms won't be stable. Rather, electrons will fall on the positively charged nuclei in less than 10⁻⁸ seconds. But the fact that we are here, we are living, means atoms are stable. And it is quantum mechanics which tells us why atoms are stable. And quantum mechanics have been verified again and again in many experiments. Today, your mobile phone, computers, lasers, they are all governed by quantum mechanics. Electronic devices will not be possible but for the fact that semiconductor devices with valence bands separated by a band gap with the conduction band, these things were not there, and these are there only because of quantum mechanics and so on. But the surprise that quantum mechanics brings in is that the quantum mechanical world, complex variables are truly the real things. That means our quantum mechanical world fundamentally has to use complex variables, and square root of -1, which is iota, the so-called imaginary number, they appear directly in the Schrodinger equation that tells us how the state of quantum mechanical system evolved with time. And there's a new constant which appears, namely the Planck's constant, that plays very important role in many quantum phenomena. And quantum mechanics is truly mysterious. In particular, I will show you some of the very magical things that quantum mechanics bring in, that is things like superfluid and superconductor. So if you, for example, cool helium gas less than 2.17 degree Kelvin, then the helium gas becomes liquid. It becomes liquid around 4 degree Kelvin, but when you cool it further to 2.17 degree Kelvin, this liquid helium becomes a superfluid, and the superfluid shows all kinds of magical behavior. It just spontaneously comes out as a fountain. And moreover, if you take a test tube and lower it in a beaker filled with liquid helium, then after some time you will find that the test tube has got filled with liquid helium. That means liquid helium simply crawls along the walls of the test tube and fills up the test tube. Similarly, if you lower a fully filled test tube in an empty beaker, the liquid crawls out and fills the beaker. So these are basically the liquid helium behaves like a macroscopic quantum mechanics. This is surprising and magical. They can be only explained by quantum mechanics. Similarly, superconductors, if you certain conductors like mercury or copper, etc., when you cool below a particular temperature, the resistance simply goes to zero. And not only that, a superconducting object becomes completely diamagnetic. If you try to put a magnet, a tablet, North Pole and South Pole will just float over your superconductor because magnetic lines are repelled from superconductors. And these are all there because of quantum mechanics. Furthermore, in superconductors, there is something called a Josephson effect. If you take two superconductors and put a thin layer of insulator, so you sandwich two superconductors with a thin layer of insulator, even if you don't connect a battery, if you just join them with a wire, you will see current flowing from one side to another side. So these are the magical things that are shown by superconductors, and these surprises can be seen, understood only by the laws of quantum mechanics, which were creatively developed by many physicists, starting from Einstein to Planck to Niels Bohr to Heisenberg to Schrodinger. Many physicists played role, de Broglie, all right, in developing quantum mechanics. Is their creativity, their new way of looking at quantum mechanics that gave us the laws of quantum mechanics. So this Schrodinger equation, you can see square root of -1, the iota is appearing here. Here there is a, as you can see, the rate at which the state of the system, which is symbolized by wave function psi, the rate at which it changes is given by the so-called differential equation, and the iota square root of -1 directly appears, and psi itself is a complex function. So in other words, our physical world cannot live without the complex entities like wave function, without the square root of -1, iota, and so on. So quantum mechanics, of course, gives rise to a lot of puzzle. I will just stop here with this puzzle, that after all, we know that universe began from the Big Bang. Initially, everything was in ionized form with fundamental particles, but as the universe expanded, it cooled down, then atoms and molecules formed, planets were formed, complex molecules were formed, life originated. Finally, through Darwinian evolution, we had human beings, intelligent human beings, and we intelligent human beings, we are all made out of quantum mechanical objects like atoms, molecules. Our brain is made out of atoms and molecules. And these quantum mechanical systems in our brain are trying to understand the laws of nature, which are quantum mechanical themselves. So that means quantum mechanical systems themselves are trying to learn about the laws that govern quantum mechanics. Here is the paradox that universe evolution, uh, the quantum mechanical evolution gave us to life, life finally evolved, gave us to consciousness, which gave us to observing our universe and trying to understand the same quantum mechanical object from our quantum mechanical brain. So this is a very, philosophically very mind-boggling. I'll stop here. I will rather take questions.
So thank you very much, Professor Patrick. There are many questions which I can see in the chat section. Would you like me to run through them?
Well, when I'm in the full screen mode, I'm not able
Maybe
to
you can just
see the
stop sharing.
chat.
Yeah. You
Yeah,
can just
okay.
stop sharing. Yeah.
Yeah, but probably
Okay, I'll
I'm
go through
able
it.
to read.
Sure, no problem.
Yeah.
I'll read it out. Let me just scroll it down.
So we can go sequentially.
Yes, I'm going
one
from
by
the top.
one.
Yes. Why does the path is elliptical only, and
Why?
why not circular?
Sorry, why?
Why does the path is elliptical only and
Why
why
is
not
planet
circular?
going around in elliptical orbit?
Yes, yes.
But circle is a special case of when equal to major axis, it's a circle. So if something moves in a circular orbit, then it is automatically moving in an elliptical orbit with zero eccentricity. So it is like saying that if I say something about living beings, it is more general. It will also, anything that is true about a general thing which is true about living system is also true about human being. For example, all living beings die, and therefore I will also die, is obvious. So similarly, if something is true for elliptical motion, it is also true for circular motion, because circle is a particular case of ellipse.
Okay. I'll take up the next one. Is there any kind of force in space that is outside the Earth's orbit?
No, there are many forces apart from gravity. For example, Earth is like a bar magnet. Earth has a magnetic field, and the near the surface, for example, we hold a compass needle points. As you know, the Earth's magnetic pole has been recently showing shifting. Now the North Pole is shifting towards the Siberian region. Earlier it was in Canada, region in Canada. So the magnetic field lines are the other forces, and magnetic field lines play a very important role because they stop the high energy particles coming from sun, the so-called solar wind, and many of the high energy particles, if they come copiously, they will cause problems for living systems, like we will get cancer and all that. So therefore, the magnetic field lines indeed are protecting us. And apart from gravity, gravity is of course long range, is 1 over r square. So gravity will always be there no matter how far you go from Earth. But magnetic field, as you know, for a dipole magnet, the magnetic field decays 1 over r cube. It falls faster with distance. I hope I have answered your question.
Yeah. I'll take up the next 3 questions one by one. Can the wrapping of space-time and its gravitational pull be explained as if an object is going straight, and then because of the wrapping, it appears as a slide, and so the object accelerates?
Yeah, so if you learn general relativity, you'll find that what happens is that when an object is thrown, whether in Earth's gravitational field or Sun's gravitational field or Earth going around the Sun, so these are nothing but the shortest possible distances in the space. So you're right that although the path is not Euclidean path, so although the path is this, not the Euclidean straight line, but this path happens to be the shortest spatial path. Or if you include the time, it is the longest path. Such trajectories are called geodesics. So in Einstein, a particle not acted upon by any other force other than gravity, they move along geodesics. Geodesics are paths that are shortest in space, but if you include the time also, they are the longest. Okay.
Okay, I'll take up the next one. This is more sort of career guidance kind of question.
Okay.
So the student is asking, I want to pursue my career in physics field. I had this doubt for a long time. Which field should I pursue for my further studies? Quantum physics or astrophysics?
Finally, of course, it depends upon your interest. So, uh, you know, even if you want to become an astrophysicist, you have to learn quantum mechanics. For example, in many star, quantum mechanics is required. In fact, Chandrasekhar, who was one of the greatest astrophysicists of all time, he became famous because he used quantum mechanics for white dwarf stars and obtained a maximum limit to the mass of the white dwarf. Today we call it Chandrasekhar limit. So the suggestion is that if you want to be a physicist, whether you are an astrophysicist or whether you want to do particle physics, work with large hadronic collider, you have to do a master's in physics. There, you have to learn all different subjects because for research, you would need all subjects, whether it's classical mechanics, quantum mechanics, electromagnetic theory, thermodynamics, statistical physics, mathematical physics, experimental physics. All these things have to be studied. And that is the reason why we offer masters in physics course where a student is given many, many different courses. Student does a lot of experiments in different laboratories because both experiments and mathematical uh, problem solving both are very, very important to become a physicist. So you can decide which area you fall in love with. Ultimately, those who become physicists, why have they become physicists? Because they fall in love with a particular area and they think that working in that gives them happiness. So you have to find out what gives you happiness. Whether it is quantum mechanics or astrophysics, in both fields, very new things are happening. For example, quantum mechanics, newer nanomaterials, graphene, new spintronics, quantum are being studied to get one information from one point reality, while in the field of astrophysics, new objects have been discovered like fast radio bursts, gamma ray bursts, etc., which are very strange objects. People still don't have a good understanding of these. So all research fields, the physicists, when you see surprising result, you ponder, you say, oh, can I somehow explain using some theoretical model this surprising result? And that's how we get the kick out of research in physics.
Okay, sir. I'll take up the last question now. There are two parts of the question. The first one is, Aristotle haven't noticed buoyancy and he got wrong. Then how
Also air resistance. He did not realize that air resistance causes leaves and feathers to fall at a slower rate.
Okay, okay. Because the second part was how Galileo escaped buoyancy when he performed similar experiment.
Yeah, for when he dropped heavier objects like 20 kilogram, 10 kilogram, such heavy objects hardly cause buoyancy or appreciable air resistance. So therefore, in his measurement, he carefully chose objects for which buoyant force and air resistance were negligible compared to the gravitational force.
Okay. So the second part was, did Einstein's theory lead to wormholes?
Wormhole.
Yeah.
Yeah. So wormholes are a mathematical solution where if you have two black holes separated by space and time, then people have shown that you can connect the two black holes by a very narrow tunnel, which people call wormhole. And this narrow tunnel is maintained by some exotic matter in the sense that in order to create this wormhole, you need some crazy matter which has negative pressure, highly negative pressure. Such material have not been discovered in the laboratory so far. So therefore, although these are mathematical solutions that follow from general relativity, if you have some exotic matter which have negative pressure, they have not been created so far because no one has ever discovered such exotic matter. That is the first thing. Second thing is, theoretically also, people have shown that even if you create a wormhole, it will be very, very unstable. The wormhole will quickly collapse to a black hole. So therefore, wormhole is a bad news, unless, of course, some other criteria, some people bring in and show mathematically that the wormhole solutions can be stable. But at the moment, the idea of wormhole is purely at the level of mathematical solution, no actual physical realization of wormhole.
Okay, sir. Okay, there is one last question. Can I be hired at ISRO as an astronomer?
Can I what?
Can I be hired at Indian Space Research Organization as an astronomer?
Hired where?
In ISRO, ISRO.
Oh, yeah, why not? I mean, ISRO has an institute called Indian Institute of Space Technology. This is an institution of ISRO itself, and IIST, Indian Institute of Space Technology, is in the city of Thiruvananthapuram. And many faculty members, many scientists, they are astronomers. Many of my friends who work in IIST, they are actually astronomers, theoretical astrophysicists, and so on. So indeed, if you are an astronomer, you, depending upon the field of astronomy that you are researching on, you can be a faculty member of IIST.
Thank you very much. Sir, there is one last thing. I think that maybe some students, they are, yeah, maybe some students, they are interested for some kind of career guidance in this area. So can we have, I mean, they are asking so many questions related to it. So sometime later, maybe if we can organize some session on career guidance in the area of physics, will it be possible? I mean, lot many students are asking this question.
Yeah, why not? I mean,
Okay, okay,
we can always have a session on
sure,
career guidance.
sure.
But since this question was asked, um, uh, let me mention that if you want to be a physicist and you want to also have a career, then those who do experimental physics, they have a better chance of finding a job in a good place, because now applied physics and experimental physics, they are being funded, and therefore if you want to be a physicist and you want to have a secure career, it is always good to be an applied physicist or an experimental physicist. But of course, I mean, this is just a summary of career guidance.
Sure. Thank you. Thank you very much, sir. And it has been a wonderful session, especially because although I expected it to be of 30 to 40 minutes, but you have taken up nearly all possible questions which the students they have asked for. And on behalf of the National Academy of Sciences, India, Delhi chapter, and the Deen Upadhyay College, I would like to thank you once again, and also would like to thank all the students and the teachers who have participated in this program, and hope to see you all tomorrow for another interesting lecture by Dr. R.S. Swati, which is on carbon membranes for separating mixture. So she is from IISER Thiruvananthapuram. Thank you very much, sir.
And thank you very much. And everyone, stay safe and take care.
Sure. Thank you very much.
Goodbye.
Okay.